All right, good afternoon. This is my great pleasure to introduce Dr. Chung, a computer scientist visiting us from IBM Research. Dr. Chung has a PhD in computer science from University of Maryland at College Park. He has been with IBM for a while, and his work focuses on all the important things related to performance, tuning for the performance, performance modeling, and also tools necessary to characterize and understand performance and improve. His primary research expertise lies in systems architectures, with particular emphasis on cloud computing and high-performance computing. Currently, he leads efforts to co-design future cloud computing infrastructures and tailor it to strategic AI, strategic applications. And you can kind of see from the title of his presentation what those applications are these days. Dr. Chung's contributions extend across various domains of system architecture, including software, including performance analysis, including tools development, and also with the focus on a number of flagship IBM architectures or systems such as Coral, Power, Blue Gene system, and also most recently Vela. In high performance computing, Coral, Power, and Blue Gene, these are sort of household names and very, very well recognized systems. And so it's nice to have Dr. Chung to perhaps mention some of those systems here too. So additionally, he also serves as an adjunct professor at the Courant Institute and NYU, and also at Columbia University, where he shares his knowledge beyond his work at IBM. So thank you very much for coming. Let's start.
Sure. So thank you for the introduction and then the warm welcome. So we also have my colleague Hubertus, who is even more senior than me online. So he will make sure that I'm talking the right things, right? So as you can see that we're at an interesting stage. It's interesting moment in the computing. So as you can see, the faster advancement in the AI, in the data, those data-driven application and the cloud technology, right? So it is challenging for a lot of previous assumptions. We're trying to see how we can do a better design, help the situation, help the user consume the technology. So in the early days, when the system scales from tens of the processor to thousands of processor, then there's some design guideline to help the user improve their application, so then they can consume the system, the cluster at a much larger scale. Similarly, later when the GPU was introduced to the picture, we start a cycle again to have a discussion with the user, learning the workload to see how the new technology like the GPU can be consumed and then introduced to the computing. So right now we believe that this is somewhere another stage, maybe looking even the next stage is coming up in the areas of quantum. So we're always in the cycles of trying to see, we see the new technology coming up, we see how the technology should be consumed and then being taken advantage by general user, not just only by a few selective computer scientists. So that's where our role is. We try to understand, on the one side, we try to understand the usage scenario, the workload characteristics. On the other hand, we try to see what would be the coming or incoming new technology that can help. So then our role is to design and build a system to bridge the user as well as the technology. So through the years, we see that in the past, usually the systems are building from the bottom up. So people come up with the ideas, put their what the best that they can do to build a server, build a system on top of it. So then up to the user to make the best use of it. But actually, the experience tells us that it's actually should be the application that drives these efforts, because should be depends on the usage, depends on the deployment, the usage scenario. That should decide how the system should be designed. Okay, so today I'm going to show you some examples through the history, what we have done in the past, as well as the recent work that we're doing in the Vela 2 system from the IBM research. How we, for example, in the latest one, the Vela 2, we try to build a high-performance system in the environment of the cloud. There are some fundamental conflicts between HPC, so-called high-performance computing, and then the cloud computing, because HPC is in the spirit of the performance, while the cloud computing is in the spirit of the sharing. Okay, so we'll talk more about that in the later slides. All right, so as I said, we want to design a system based on the intended application. So usually, even in the class, I usually use a car as an analogy to the computer system. We're building a computer system. You think the computer system is like a car. It's just like when you build a car, you really want to know how the car will be used before you put it into the design. You can build a car for racing, which is probably performance driven. And then in order to win the car, win the game, you are willing to give up something, right? So being comfortable, being able to carry a lot of things, that's probably not on your concern list when you build a racing car. But on the other hand, if your car is designed, let's say, to do grocery shopping, maybe you need to make it fuel efficient. Maybe you need to make it easy to maneuver in the street. So then it can serve its purpose. And of course, there are something in common as well. With both of them, either it is a racing car or it is a grocery shopping car. You want them to be safe, right? So there are some considerations when you design the system. So when we design a system, what would be the question we would ask first is what would be the objective? What would be the target? Are we trying to build a system so that we can help the domain experts shorten their time to the solution, or maybe to handle larger amount of the data? Or for today's, the energy efficiency is another concern. Can we build a system with a higher energy efficiency? So why do we want to do this from the application point of view? Why this application-driven design? First of all, this requires cross-discipline collaboration. You need to have that expert from the user. You need to have the expert from the technology side, and then you need to have the people who can do the integration. So this is going to be a collaborative. And not just that, this kind of a collaboration is not going to just be one shot of effort. It's going to be iterative, which means through the iteration, then things can get better and better, because sometimes the user doesn't know what they want, while the technology provider doesn't know what needs to be there in order to help the user. So to achieve things like that, we want to have the performance mindset, which means we want to keep the system efficiency and effectiveness as the guiding principles through the design process. And then this is going to be a continuous optimization. So the point is, from the functionality to the performance, we really need to know how the system will be used. The challenge of designing the system is that what we have today is what we have the current computer system, we have the current application. But the system we design usually need to look ahead. Maybe the system will be delivered in 3 years. Maybe the system will be delivered in 5 years. So the goal is we want to design the future system. But remember, some technologies are still being developed, right? So what we have today may not be what we will use in the future when we deliver a system. On the other hand, from the user point of view, what the user is running today is still evolving. Based on the technology, based on the domain requirements, it will evolve towards its target. So we see cycles like this happening a couple of times. So for example, when the GPU was trying to be introduced into the system, the GPU at that time, the V100, Volta 100 was being planned, and then it's not delivered. As well as the code was not written with the GPU enabled. So with these kind of situation, how do you build a system so that it will reach the performance target? So things like this, we need to know, of course, the planned usage of the application. On the other hand, we need to know the potential technology improvement. So the way it worked out through the history is that we start with the so-called proxy applications, which means those proxy applications including some skeleton or micro benchmarks. And then some ideas or some exploration for the new incoming technology. Things like the specs provided by the vendor. And then, of course, in the house, what we do is we start with the pen and paper estimation. We start with some real measurement based on what we have today, what we expect as a projection for performance in the future. So this is sort of the challenge we're facing. The point is we don't have what we deliver when we do the design work. It has to be estimated, projected, and then even things like the performance measurement, performance modeling, all these things need to be in place in order to achieve the goal. So one thing we did is trying to understand the application characteristics. By characteristics, I mean the type, the amount of the resource that needed by the application. So the chart on the right-hand side, just a conceptual one. You have in the web chart, different dimension means represents different performance metrics, performance measurement, and then different lines are representing different applications. So the data point is outer in the boundary of the web chart means that it's need high in that metrics or the high utilization in that component. So you can see different application. This one just give you an idea. Different application will have different characteristics. So this is things that we need to know. Back to what I mentioned in the beginning is we want to know what will be the planned usage, what will be the requirement for each application. Things like some applications are having high communication ratio. Some applications have the high floating point operations. So they will require different resources. And then we need to have that in mind when we design the system. So these are the things that we go through when we try to understand the application better. Starting with the functional analysis, try to know what kind of core functions are or what kind of algorithms are there. As you can see in the HPC area, there are different computation kernels, maybe computational fluid dynamics, CFD, maybe faster Fourier transform, things like that. We all need to have some ideas about what the workload requires. So then the resource requirements, as I mentioned there, things like how much CPU, memory, storage, bandwidth, things like that are needed. And then on top of that, what will be the usage patterns? Basically, you want to consider the time factor, how these resources are required over the time when the job is running. And then what about the data side? What kind of data type, the volume, the access pattern? We also need to have some understanding. All right. And then, so the performance, including what will be the objective. When you are doing the training, maybe you want to ensure reasonable time to solution. When you do the inference, maybe you need to ensure the reasonable latency, things like that. And then last thing, but not the least thing is the scalability. How do you scale up to the scale that can be practical and then useful to the domain experts? So this is in the area where we start with try to characterize the application characteristics. So through the time when we try to understand the application characteristics, we work with the workload stakeholder, and then we do things like, because remember, the workload itself is not static, it is still improving, it is evolving and changing through time. So to help these workload adopting the new system design, the new technology, the workload needs to evolve. And then we work with the stakeholder to improve the situation. But this is kind of in this area of the performance diagnosis, the tuning. So we want to know not just the characteristics, but what kind of a transformation, what kind of changes are needed in order to not just enable the application on the target platform, but also to make it perform on the target platform. So things like that, it requires the people doing things like this, requires the knowledge in the wide area of algorithm architecture, compiler, runtime behavior, and then you need to spend quite a bit of time trying to collect, understand the data. So this is one just give you some idea. The data, the performance data, the characteristics we're getting are actually coming from everywhere in the system, from software, from hardware, software, program execution, maybe the source code, maybe the compiler. Actually, there are quite a wide variety of the performance data that we can collect and then start to do the analysis. And then this is the figure on the bottom right shows you the iterative process, which means when you start in the top middle, where you have the application finally enabled and running on the existing system. So you start with the profiling, with the tracing, you figure out the application characteristics, followed by some analysis, trying to figure out what's going on there, like the bottleneck. And then you may have some hypothesis that says, oh, because of this, because the access pattern is not right, because let's say the SIMD instruction is not SIMD instruction unit is not utilized well enough, then you need to have some ideas how you can improve the situation. So the improvement can come from two ways. One is to change your application. So then your application will be, let's say, with different access pattern, better use the system. Or this kind of analysis also provides as a guidance for the future system, which means in the future, since the current system is used this way, why don't we, for example, improve the bandwidth? Why don't we put more resources to improve the bandwidth to address the issue? Right. So then this kind of implementation will make you back to the start of the cycle again. If it goes well, then you move on to your next target. If it doesn't work well, then maybe your transformation is not working right, your hypothesis is incorrect, then you need to go back and think about what's going on. So the point I want to make through this slide is the application is evolving, even from our job point of view. We try to work with the stakeholder. We try to help them not just enable the application on the target platform, but also try to help the workload perform well on the target platform. So let me start with one example, which is you can think it as an old problem, but it still exists even as of today in the environment of the cloud computing. So the question is, or the challenge is, in the large-scale systems, as I say, whether it is HPC or the cloud today, when you run a large-scale job, how do you map your tasks onto the physical nodes? Because it matters a lot in terms of the performance, especially from the communication perspective. So from our point of view, to work to provide some kind of assistance in this space, in the design, is that we want to have some kind of a tool that can automatically and efficiently generate the mapping file to support things like the MPI jobs. Okay? Because from the domain expert point of view, when they convert their problem into the program, they may, in order to run at a scale, they need to divide the problem into tasks. And then, for example, let's say doing the climate simulation over the continental US, you may want to divide the space into the subspace. Each subspace is converted into a task or a process, then running on a large-scale system. There's a reason why two tasks are adjacent to each other from the problem domain, because maybe they are adjacent to each other in the space. In the space. But then the thing is, if you don't plan carefully regarding to the mapping, then situation will happen like this. So let's say just for 1D array. So you have, let's say, 9 tasks. And then if you just map in terms of enumeration, then things that go like this. So you will have 0, 1, 2, and then because of the hardware cluster topology constraint, the next task will do the round robin and then be being placed far away from the previous one. So 2 and 3 are adjacent to each other in the problem domain, but they can be away from each other in a host machine domain. A better mapping, as you can easily imagine, will be on the right-hand side. Instead of a round robin, maybe you need to fold it or twist it, but just don't break it. So this is considered you take it apart and then put it far, far away from each other. While the right-hand side is more like you fold it, you don't break it. So then some kind of locality can be preserved. 2 and 3 are adjacent to each other in the problem domain, and they are next to each other on the host machine. So this is are needed and then should be transparent to the end user, because the user.
So I-Hsin, how this is different from the data paradigm, tensor paradigm we apply in the machine learning system?
So how is the question is, how is this different than the tensor or the data paradigm?
Of course, data paradigm, tensor paradigm, we are also going to map the machine learning tasks to a low-level GPU node, right?
Right.
So how this is
So I would say this will have a lot of a similarity in that space, because for right now, of course, it's probably This is probably, this was coming from the Blue-Jin homogeneous CPU-only kind of a scenario. Right now, I'll show you the next slide with some ideas, actually, that is being applied for today's tensor data parallelism in terms of the mapping. But the concept is just, as I said, how you place the task properly. So then the performance will not be affected seriously. But for things like that, actually, through this part of the work, what we came up is, the one I just explained, fold and twist kind of thing, is more like the static map. So it's, as long as you have the topology information of the problem domain as well as the host domain, I think we can come up with a fancy algorithm, how you fold it, how you twist it, and so you will map it nicely onto the host machines. But what things can be done here, to answer your question, is more actually the things that we came up at that time is more on the dynamic mapping strategy, which means, can we do some measurement? And then based on the measurement, can we partition, for example, the groups? So then within the group, they communicate more. Across the group, they communicate less. So with that kind of a principle, we can also map the problem nicely. So for example, for those different parallelism in the machine learning today, I think the common practice, as you can see today, is for the data parallelism, because they are considered loosely coupled. So usually you put in maybe different tensor data parallelism groups into different racks, while the pipeline parallelism and as well as the tensor parallelism usually involves more traffic. So then you try to map that within the server using the higher bandwidth interconnection like the NVLink. And then for the pipeline parallelism, you map them across the server, but within the rack, because they share the top of rack switch. So depends on how much traffic are needed. And then if you push this to the extreme is you can even try, because in the context of the cloud computing, the network may be shared. So you may want to even measure the traffic, and then based on the measurement, you do the partitioning, you do the mapping, which is potentially doable, but depends on, again, what's the overhead to do this measurement? What's the overhead? Let's say you need to reshuffle the workload. Maybe you cannot do that frequently, depends on the overhead, the implication. Does that help you?
Yeah, yes.
Thank you. Right, so with the dynamic one, this is later with the dynamic one, try to do things like you do the mapping, the measurement, and then you start to do the partitioning. So we came up with some simple ways to do the partitioning based on the task. So with the tasks that talk to each other more often, we group them into a group, and then you do similar thing on the host machine to group the, let's say, the processors. And then you map the group of tasks onto the group of processors. And then you can do this actually in a hierarchical way. So within the group or within that group of processors, you can further refine it to do the partition again, and then you map it to the part of the host machine. So then for some mesh communication workload, you can easily see the benefits of things like doing things like that. So the communication time on the y-axis is always better, and then you have different configuration. At that time, these are like a dual core, quad core, what's the scale, how many number of nodes you have. So with the mapping, you can, I think even intuitively, you can see the improvement that can be achieved through things like this. So another example, even in the HPC timeframe, this is the example which is interesting in terms of changing the hardware to help the application. So the idea at that time is called the listed data prefetching. So the challenge is prefetch caches are very effective if you have a strided memory access. But then it performs really poorly when you have a random access path, okay? Because from the hardware point of view, think about that if it can predict what the data element is needed, it will be able to prefetch it for you. But then the thing is, if you have if your access pattern is random, then it is difficult to prefetch the data for you. And then, but this kind of a random access patterns actually is existing in a lot of places. And then as you can understand that it will be difficult to optimize the situation. So for example, you say, no, I don't write a code to have the random memory access. But then the thing is, things like this. So the most trivial one is the pointer chasing. So let's say you have a two-level nested array. So you have array B with the index variable J. And then the element of this array B is used as an index for the array A. So when you try to access the elements in array A, even you sequentially increase the number of variable J, the elements of array A is access random, right? So other example like the hash table lookup, sparse matrix operations, or you do the page walk in the virtual machine or some dynamic graph algorithm. So basically you will have a lot of situations like the bottom one. So when you walk the memory, oftentimes you will have random memory access instead of a sequential access. So it's an interesting problem. And then how do people improve the situation to help the design? So at that time, what we did is we tried to so-called list prefetch engine. This is a piece of hardware that we're working with the hardware design people. They put it into the hardware. So then it will, with the hardware design, that including things like the cache, and then it will, the idea is it tries to record these kind of a random memory access pattern, because these things will repeat over some period of time from many applications. So it tries to prefetch the data based on the recorded memory access from the previous iteration, maybe. So then the design was with one is kind of a list prefetch engine per hardware thread. And then to help the user then it allows some configuration, such as the prefetchable depth. And then these kind of addresses are recorded, stored in the memory. And then with some API provided to the user can actually control through the API. All right. So the way it works will like this. There's a sliding window because there's a limited resource that you can try to do the match and then prefetch. If it matches, then this sliding window. So this list records the addresses from the previous iteration, and then it tries to play back using the sliding window. If there's a match, then the window will just move forward. If it does not match, then you will stay around, and then it will try to prefetch what the size of the window that provides. So because there's another consideration is maybe even if the access pattern repeats, it may not be identical to the previous iteration. So it needs to allow some error. It needs to tolerate some prefetch, right? So then the design also says if you miss too many times, then this mechanism will just be given up. The prefetch engine can also be paused, it can resume, things like that. So through this, then for some workloads, as you can see that with this kind of needs from the application, doing the design in the application, we did a lot of performance study. This is just one example, says with this kind of a prefetch, how much improvement can we get? So these are different threading configuration. This is the time, lower is means better. And the color part shows the results with the list prefetch engine enabled. And then together with some policy in the system software says how aggressive this prefetch needs to be done. Can it be as aggressive as it, which means try to prefetch as much as you can based on what the window allows? Or it says you better make some kind of a confirmation that your prefetching is confirmed, which means it's valid. So then you can see being too aggressive actually is not a good thing. If you can have some kind of a confirmation before you refresh the data, actually that was the best. So with the replay of the memory addresses as the prefetch target and the confirmation of the prefetch results, you can achieve quite well in terms of the performance. Okay, so then these are just some more details about the workload and then how things can help. That was an interesting project put into the design to help the user. Okay, I think this part I will probably skip because of the time constraint. I want to talk more about then after the HPC era, I started to work more on the composable system side, trying to build a system. So the idea is, since there are different requirements from the previous discussion, as you can easily see, the user will have different requirements, the workload will have different characteristics. How do we design a system to be flexible enough to accommodate different workloads? Because previously, for each of the workload, whether it is the traditional one, which is CPU only, or together starting to have some accelerator like the GPU, or like machine learning, which requires more and more GPU resource. Previously, usually the system design is static in the sense that to serve each of our workload well, you need to have an individual design, which can be siloed, right? So as you can see, these will be the workload characteristics. And then if you map that into the hardware resource, this is the middle column row here shows you the topology, right? The CPU is the red, the communication is sort of blue here. And then these are different server design in order to serve different workloads. So the challenge is, can we have a system which is flexible enough to satisfy each of the workload well, right? Because some resources are very valuable. So for example, GPU, as you can all see that it is expensive. If you put it into the static design serving the specific workload, when that job is not running, a lot of the time the GPU can be idling, and then that will be a waste of resources. So how do we maximize the utilization of the expensive system resources like the GPU? That was the agenda, okay? And then the idea is, why can't we have this kind of a design that you put the resources into individual resource groups, and then those resources are interconnected with some kind of interconnection. And then these interconnections also connect to different basic hosted servers. So which I represent you here as the CPU with red. So these are just simple CPU with red. And then the switches are not just the, for example, we use the PCIe switch, which is not just, at that time, it was not just the wires on the board. We used the physical PCIe switch connect to external enclosure. In the external enclosure, you can think that some enclosure are loaded with the network card, some enclosures are not loaded with the GPUs, some enclosures can load it with the storage. So the idea is, through the configuration of the routing of this interconnection in the switches, we can assign different resources, some resource components to specific server. So this is happening by changing the routing in the switches. So for example, in this one, you can see this bunch of the GPUs are configured to belong to assign to this host. So conceptually, what user sees, now user has a system configured with the GPU, the number of GPUs, the number of storage, as well as the number of network cards needed. But physically, it will be something like in the top. This is configured in the system software level. This is what the user will see, right? So in this way, if this is successful, then it is quite attractive because I can, from the provider point of view, I can reshuffle the resources to different hosts based on the user requirement. This opens a new dimension actually in the scheduler. So the scheduler can not just find the good configuration for the job, but the scheduler should be able to configure the system to specific jobs. right? So this is the implementation at that time. This is the middle one here are the PCI switches. So at that time it was only PCI Gen 3 switches. The yellow ones are representing the accelerators, while you have some storage as well as some network cards other places. So these are network cards, while these are the PCI switches. So you can see within the enclosure that you can host these number of the GPUs together with the switches inside, some storage inside, and some network card inside. Through the configuration of the switch, you can assign these GPUs to one of the hosts, while the network card to another host. And then with this kind of a thing, you can satisfy, for example, the two workloads in the top, right? Or you can change the configuration again. So then you can partition the resources within the enclosure, and then to satisfy the other two workloads. Okay, so it was an interesting project. And then, yes.
I'm curious to know how important it was to take into consideration the disaggregation of the physical resources. So say your schedulers or your servers and stuff. Do they also have to consider how the physical placement of these resource pools as well, or was that not as big as problematic?
So then let me clarify the question. You're asking the placement of the resource.
Correct.
How important is that one? I think it's always important to consider the placement of things. But even before you have the placement being considered, you need to have the resource. So this is trying to help you even in the lower one, says, how do you provide the resource to the user? So then the user will continue to consider, for example, you have two CPU here, where you should run your job, who should deal with the GPU, who should talk to the storage, and then talk to the network cards. So I would think that in a different layer. So this is trying to help you in the bottom one. Okay, so of course, through things like this, we learned quite a bit. At that time, actually even until now, it is, I think right now recently there is a momentum trying to revive this project because we see more and more needs in this area. The lesson we learned, actually, I can share that what we learned through the years in that project is that it looks interesting. Of course, it looks interesting because it's flexible. Now you have a server serving different workloads. But the lesson we learned is it's somewhat related to the quality of the design or the reliability and availability of the design. Because let's say you're running a GPU cluster, you want to set up a GPU cluster. This, of course, attractive, but then the challenge is you need to think about when it doesn't work, when something fails, then suddenly you will have a cluster without a GPU, for example, right? So the lesson we learned is this kind of good design can be used as a reinforcement, but may not be a great idea to use it as a backbone. You use the backbone, when it works, great. You have all the flexibility. You can, as dynamic as it can be to serve all the workloads. But the challenge is when it doesn't work, something goes wrong, then suddenly you lose all the devices. You are left out with a bunch of servers, right? And then you don't have the resources. But it also opens other opportunities. So things like lifecycle decoupling, which is always attractive from the system administration point. Because with this kind of a disaggregation, you can decouple the life cycles of each individual component. When you upgrade, you probably don't need to upgrade the whole server farm. You can upgrade the component as they are in a resource pool. And then furthermore is, because of sharing the resources, it opens the opportunity for direct data path, right? So previously, you have two servers. Each server has its own GPU. Now you run large-scale training job. The GPU needs to talk to each other across the server. What do? Somehow you push the data from the GPU to its own network card, over the network card to the target server target server NIC to the target GPU. But now you have shortcuts. In this case, for example, this guy and this guy, actually they share physically these switches here, even though they belong to different servers. But if you enable this kind of a shortcut, then the data transfer will be much more efficient instead of going the long way. The analogy is when you send a mail from you to your neighbor, of course, you go to the post office. Or if you know the shortcut, you just pick up the mail from your mailbox, put it to your neighbor's mailbox, then your mission is accomplished, right? So these things like this, it opens a lot of opportunity. So similarly, instead of network cards, and instead of the GPU, if these are network cards, if they are in a semi-enclosure, then you can just have them talk to the shared switches. Okay. So then we continue to work into the AI workflow. So this is probably well known and common to a lot of people already, trying to figure out what are required in terms of the AI workflow, right? So you can see different stages from the data preparation all the way to the training, then fine-tuning, inference. They would all have different requirements in terms of the computing resource. There's some analysis trying to figure out where this need to happen. Is it on-prem, like in the private cluster, or is it in the public clouds? And then eventually, in terms of the amount of time, amount of resources needed, it's all different. And then, so the Vela 2 project is our attempt trying to design an HPC system in the cloud computing. So if you start to look at it, there is some fundamental difference. As I explained before, is that HPC looks for performance, while the cloud is look to share. And then these kind of thing, HPC requires high performance, and then the task with the low latency, with the massive parallelism, while the cloud is trying to design for flexibility, for scalability, and then with the resource pooling. So how do we design a system that have the best of both sides? That was the challenge, right? So as you can see here, there's something, of course, in common in terms of the for example, hardware resources, but there's still something quite different, right? In terms of the spirit, in terms of the abstraction, here more on the file system side, while on the cloud side, you have different storage, whether it is block storage, object storage, of course, file storage. So how do we design a system which they're quite different in terms of the capabilities and then assumptions? That was the effort. So we want to have an AI system in the cloud environment. The idea is we want, for example, we want the flexibility. So we want it to be container native, software-defined AI cloud platform. And then to put this system in a cloud context, it needs to use, for example, we wanted to use the Ethernet as contrast to most of the HPC system is using InfiniBand. And then, so there are some requirements if you want to put it into the existing data center. We want the HPC performance, as I mentioned, but we wanted to work with the cloud native, for example, OpenShift stacks, and then which is managed through the standardized cloud APIs. So with this kind, hopefully with a good design, it will allow things like the seamless resource reallocation. And you see from the previous workflow, hopefully with some kind of reallocation resource management, it can optimize for different sizes for this diverse AI workloads. And then with this kind of thing, hopefully it will provide accelerated model development. But on the other hand, similar to HPC, we really want to provide some visibility. So then we know that what's going on there. And then that can help us, as well as the user, understand the performance characteristics, as well as the system utilization. So to achieve things like this, it actually requires co-design across different layers, right? So from the top layer, how do we build and optimize the runtime library that can take advantage of the infrastructure. So for example, you need to think about from the FSTP, TTP, what are needed from the bottom to support this. For example, when you do the communication, do you need some information regarding the topology? Because in the cloud, when things are virtualized through the hypervisor, a lot of low-level hardware information are filtered out. And then they may not have the information, but without the topology information, how do you do the communication efficiently? And then in the middle layer, for the cloud platform, how do you enable the performance through the cloud software, like the container? Because remember, the spirit of the container is to be self-contained, try to be portable. How do you make it with a high performance? And then for the infrastructure, how do you virtualize it? There are so many ways that you can virtualize the resources. What would be the right way, right consideration when you do the virtualization? So for example, you can put many virtual machines on a bare metal. Is that a good design? You can virtualize the GPU or the storage into small partitions, and then give them through the hypervisor to the virtual machine. Are these a good design? So what will be these are the opportunity doing the code design across the the layers. So then through the communication side, we start with just a TCP. So the TCP, the blue line here just shows you the traffic, the network traffic path that from one GPU to another. So basically you upstream to the host, and then you downstream to the network cards, across the server, to the reverse way, all the way to the destination GPU. And this is the beginning when we start to have the Vela running by the IBM AI community doing their training. And then later, we start to improve the data path using the Rocky and GPR. So then the traffic will just trying to take the shortest path from the GPU peer-to-peer to the network card over the switch to the destination NIC, and then to the destination GPU, right? So doing things like this, you can actually improve quite a bit in terms of the network throughput, 2 to 4 times better. In terms of the network latency, it's about 6 to 10 times better. So one important lesson actually through this part of exercise is, of course, enable the performance capability of the system. Another part is, a part of that is how do you deal with the data path? As the GPUs are getting more and more powerful, how do you enable the direct data transfer? So that will help the situation. So this is another, okay. So this is another one that try to improve the situation. So the quick answer to this part is through a lot of efforts like this, we're able to achieve quite close to the bare metal performance. So this is one example regarding tuning the network. So starting with the TCP, enable the Rocky, and then together with Rocky with the GPR. So in the beginning, without doing anything, using one network card, these are the numbers, the bandwidth, the gigabits per second that achieved. This is the BM stands for bare metal, VM stands for VM. So you can see it's going to be quite miserable, right? From bare metal, you're supposed to achieve high bandwidth, but when you put everything together in make it work, will it work? Yes. Will it perform? No. It will perform miserably, as you can see. But through the efforts like this, how do you, for example, doing the device pass-through, doing the virtualization, aware the host configuration, things like the jumbo pages, and then you do the efficient pass through the SRLV device, PCIe topology information through. Actually, at the end of the day, at the end of the efforts, we are able to achieve quite good performance. You can see all the way here, right? So it's quite comparable. So the performance at the end, we think that we achieve about 5% difference in terms of the virtual machine compared to the bare metal. So that was quite interesting. quite an achievement. Yes.
How will the virtual machine be better than?
That's a good question. So the question is why these guys are bad, right?
No, like, why is the virtual machine performance better than the
Which one?
bare metal?
This one. So we spend some time to look into it. We don't have the definite answer, but the speculation is through things like the buffering, through things like the caching. We suspect that was the answer, but it's so far I don't think we have the verification yet. Because the virtualization, there's something that you can keep in between. So that's the main suspect, even at this moment. But that's a good question. Okay, so another things that we observe when we build up the system is sometimes, of course, just like any component will fail. If you just fail completely, in this story, it's actually better because it's easier to catch. When your job run and then your job crash, whether your code fails or your hardware fail, then the job stop. That is actually easier to catch. But through the time, what we learn is sometimes it does not crash. It does not have the hard crash. And then job will continue, but somehow the progress is getting slower and slower, or sometimes, or even few occasions, we see that the results is incorrect. So that triggers how do we deal with the situation? So as I mentioned, the hardware, if it is a hardware failure, those hard crashes, whether it is this category or this category, it's actually easier to catch. But these software failures, for example, we observe so-called PCIe link degradation. The link quality just goes down. But then, because of the protocol, it will just downgrade the bandwidth utilized. So from the high-level job execution point of view, let's say you're doing the training, the job will continue. But then after a while, maybe in experience after like a week or two, people realize why it is much slower than expected. That was the issue. We also experienced things like the GPU generates not a number. Usually that's an exception. But then the thing is, in this existing design, the job will continue to run. Then it becomes a situation where you have garbage in, garbage out. If you don't spend efforts to catch that kind of error, then valuable resource time will be wasted. So that triggers the so-called health check, which means there's some kind of mechanism that try to do the check, whether it is you can do continuous check, but this can be invasive, which means you will have a direct impact in terms of the existing workload, in terms of the performance, or people are trying to do it in a non-invasive way, which means, for example, you do some bring-up check, the pre-flight check, to see if the components are not just functional, but also performing with the desired target range. And then in flight, how do you stick into some kind of a checking while the job is running, as well as post-flight check that try to figure out, based on the log, based on the results, trying to figure out what's going on. So that contributed the project Autopilot, which is upstream to the Red Hat, trying to help the monitoring, the health check of the system. So this is another thing that we generate through the
What do you mean by H-spin memory node? Why is that related to software failure? The last bullet in the root cause here.
This one, because this one at that time, this one is still, we didn't figure out the root cause of that one. We only observed that one. And then the effort of this part is trying to see how we detect that one, and then what will be the mitigation for that
Are
one.
you saying that suddenly the data get remapped to different addresses?
We suspect that, but we don't know. So I think I only have a few minutes left. These are the things that we're working on at IBM Research in the department I belong to right now for the hybrid infrastructure. So one of the work is to continue the optimization across the full stack, focusing on the AI workloads. Also look ahead to see what would be the future AI systems using maybe alternative accelerators. And then another part of the effort is, you know, that IBM has its own accelerator called Aspire. And then we're also trying to help to set up the design server. Right now there's a plan for the server delivery to the customer. And then the third part of the work is in the department is so-called the content-aware storage, which means think about that the storage is getting smarter and smarter. When you previously you throw some information to the storage server, you will just try to keep it. Later it was improved as it will to help you to organize the data so you can search better. Right now is can we make it even smarter so then that imagine that the storage server knows and learns what it is storing. So that was in the area of the content-aware storage. So that's another things that we're working on. And in terms of the collaboration, this was a piece of work. I work with Professor Weiman, who here trying to trying to expand the GPU memory with the storage. So it's called the big accelerator memory. The idea is trying to put the GPU out of the orchestration between the data communication of the GPU and the storage, because you want to overflow the data from the GPU memory to the storage. Normally, CPU needs to be in the middle to do the orchestration, but if the GPU is equipped with the file system knowledge, then the GPU can initiate this communication directly to the storage. And with that one, GPU through the peer-to-peer communication, the GPU can utilize the storage as the extended memory. Okay, so this is useful for workloads like the graph analysis as well as the graph neural networks. So this band big accelerator memory project not just increase the GPU efficient memory capacity, but it also reduce so-called I/O amplification that improves the application performance. All right, so the last, I'll just talk about this quickly. Things like this is we all see that traditionally CPU is the center of the server, and then the interconnection with the server is the PCIe tree topology. An interesting topic we're discussing is, can we have an alternative topology to help the situation? Because you see the technology like the DMA, you see the technology like the GPU direct peer-to-peer communication. Even NVIDIA creates its own path to interconnect accelerators like the NVLink. Basically, this tree topology rooted at the CPU is a bottleneck, and then people are trying different ways to avoid it, try to have a direct data path. As I mentioned, direct data transfer is important to achieve good performance. So is there any way we can have an alternative topologies to help the situation? It is some of the similar things are already there, as you know that like the FPGA design inside is like the 2D mesh. And then even the composable system that we design has the cross network across the PCIe switch. PCIe standard, based on my understanding, it doesn't define that it has to be a tree. So it can be a different topology. So would it be possible to have this kind of a different design, which can change the, interconnection within the server. Another topic that of interest that we're discussing is, as GPUs getting more and more powerful, you probably heard that there will be each GPU can consume like 1,000 watts, which is very, very power hungry. These are with a high circuit density, high wattage, heat dissipation. They may cause the issue, but the thing is, can we have, instead of pursuing a similar path with a strong cores, can we have massive but weak cores? So which means, think about, instead of a big elephant, can we have an army of ants? And then that can be used to as the computing environment to help the workload, right? So, but this will, of course, will trigger new problems like the hyperparallelism, scalability, elasticity, fault tolerance, like this. But this is just some thoughts that I'm discussing with the colleagues to see, well, are there opportunities like this, right? Instead of continue to pursuing stronger and stronger cores, can we have a massive but weak cores? All right, so this is my last slide. We talk about application-driven design for the computing systems. It is an iterative process, and then it requires expertise across the full stack. I show you the Vela design that try to put HPC in the cloud. How do we balance the performance, the flexibility, and then some thoughts about what would be the potential future generation servers. And that concludes my talk. I know that I'm probably the one between you and your lunch. But thank you for your time. Thank you.